Hello Year 12 Mathematics students. Welcome to this video on limits and continuity. There's a few key definitions and ideas to get your head around in this video. So we'll go through them as thoroughly as we can and have a look at a couple of examples as well. So limits. Limits allow us to describe, well, quite a few things. The way you can kind of think of a limit is we're trying to investigate what's happening as an x value or a function value kind of approaches a certain number. And so often limits allow us to do things that we can't do with just normal algebra or normal substituting numbers in. For example, when we think about graphs that have asymptotes, we know that they get really, really close to certain values without ever reaching that value. So thinking about limits allows us to think about how things are changing and behaving as we approach particular values. So this is just one example that we're going to look at here, but we've got a graph of f of x equals 3x cubed minus 6x, so a cubic graph here. This statement here says if we approach x equals negative 1, right, which is x equals negative 1, which is this point here on our x-axis. If we approach x equals negative 1 from the left, the value of f of x, right, the value of the function, or in other words, the y value, is approaching 3. And that's like saying if we were sort of coming along this line from the left-hand side, as we get closer and closer to x equals negative 1, this graph is getting closer and closer to the point 3, the y value 3, okay, as we approach from the left-hand side. If we approach x equals 1 from the right, f of x also approaches 3. So in other words, if we're coming from the right-hand side of this graph and we come down here, then back up, and as we're getting closer and closer to x equals negative 1, our function is still, and I'll probably make a meal of this, but our function is also from the other direction approaching a y value of 3. Okay? And so we can think of this like kind of intuitively just by thinking about going along the graph like we just did then. But we can also write this using notation. We can say that the left-hand limit, so the limit as we came from the left-hand side there, is written as, so this notation here says the limit as x approaches negative 1 from the negative direction. So the limit as x approaches negative 1 from the negative direction of 3x cubed minus 6x is equal to 3. It's just a really technical way of writing what we just saw intuitively on our graph. And the right-hand limit is written as the limit as x approaches negative 1 from the positive direction, so you can see that little plus there, of 3x cubed minus 6x is equal to 3, because as we approach from the right-hand side, the function, or the y value, also approached 3. So when the left-hand and right-hand limits as x approach a particular number, a, are equal, we say that the limit as x approaches a exists, right? So basically, if you're going along a graph and from both directions you're approaching the same point, we're going to say that the limit at that point will exist. And we write that as the limit as x approaches negative a, that's a bit of a typo there, it doesn't help. We say the limit as x approaches a from the negative direction of f of x, if it's equal to the limit as x approaches a from the positive direction of f of x, then that will just be the limit as x approaches a of the function f of x, okay? And this is probably, you can use this little sort of minus and plus symbols to talk about coming from the left-hand side and from the right-hand side, but the vast majority of the time you're going to use this notation to represent limits, okay? If, just before we move into some slightly different examples, if f of x approaches the same value from the left and right as it just did in that example that we saw before, then what we can do is actually find the limit quickly by substituting x equals a into the given equation. Okay, so that's really useful. That would be that the limit of f of x as x approaches a is just equal to f of a. A lot of the time with limits you can work out a limit just with substitution, with some exceptions, and we're going to see an exception in a moment. All right, so for example 26, there's like a lot of complicated ideas to understand with a limit here, but the way that we evaluate limits is sometimes really easy. With example 26, this is saying to find the limit as x approaches 3 of this function here, 2x plus 1 times 3x minus 2. So all we're really trying to think about is what will the y values approach, or what will the function values approach for this particular rule when x is equal to 3, or when x is getting really close to 3. Now, there's nothing stopping you from actually just substituting x equals 3 straight into this rule, and that's exactly what you do. So for all that complicated stuff we were just explaining, this is really just 2 times 3 plus 1 times 3 times 3 minus 2. So 2 3s are 6, plus 1 is 7. 3 3s are 9, minus 2 is 7. And that's just equal to 49. So that's a pretty simple case where all we've had to do to evaluate the limit is substitute the value of x in. Can get some trickier cases, and that's what's going to happen in this second one here. Find the limit as x approaches 5 of the function x squared minus 7x plus 10 over x squared minus 25. Now the difficulty here is if we were just to sub x equals 5 into the expression, let's look at what would happen to the denominator. We would get 5 squared minus 25, which would give us 0. And we know that in maths we don't like it when we divide by 0. In fact, we just can't do it. So we've got to do something else before we can just substitute 5 in. Because if we sub 5 in, we're actually going to get an undefined value. This function is not defined when x equals 5. But the limit is asking us to work out what does the function approach when x approaches 5. Okay, so there's a subtle difference there, but it's not just substitution. So first thing we're going to do is rearrange this a little bit, and we're going to say that it's the limit as x approaches 5 of, well, what can I do to the top and the bottom here to maybe do some cancelling, do some simplifying before I can sub the number in. And actually the top and the bottom of this function, or this fraction I should say, can both be factorized. The numerator can be factorized into 2 brackets. We need numbers multiply to make 10, add to make -7. That would be -2 and -5. The bottom is a difference of 2 squares. So x squared minus 25 factorizes to x minus 5 times x plus 5. Now we've got an x minus 5 on the top and the bottom. We can cancel those, and what we're evaluating now is the limit as x approaches 5 of x minus 2 over x plus 5. And now we can just substitute x equals 5 into this expression to work out the limit. In other words, to work out what the y values are approaching as the x value approaches 5. And we get, well, 5 minus 2 over 5 plus 5, we get 3 over 10. Right. So this function was not defined for x equals 5. So we couldn't just say when x equals 5, y equals 3 over 10. But what we can say is that the x values approach 5. As the x values get closer and closer to 5, the y values of this function are getting closer and closer to 3 over 10. Okay, that's what we've established there using the limit notation. As we talked about a little bit before, just this extra note here, if the left-hand limit is different to the right-hand limit, then the limit as x approaches a will not exist. So if you had a function or a graph where as the, maybe you've got this graph here and it's a hybrid function, and as you're coming from one way here, you're approaching that number, but from the other direction, you're approaching a different y value. If you're not, if the values of the function aren't approaching the same thing from both directions, then we would say at this point here that the limit does not exist, where we've got this gap. And that's really nice because then you get to quote Mean Girls and say the limit does not exist. So, going into a little bit more of an explanation about being continuous, and this idea of being continuous is an important definition. We say that a function is continuous at a point, and let's just say we're talking about a point where x equals a, so that can really be any number, if the function is defined at x equals a, so the function must be defined at that point, and the function must be approaching the same thing from the left and the right at that point. In other words, the limit at that point, x equals a, has to exist. Okay, so in that notation that we introduced just before, this is like saying the limit as the function, the limit of the function as x approaches a from the negative direction has to equal the limit of the function as x approaches a from the positive direction. An informal way to describe it is that a function is continuous over an interval if you can draw it without lifting your pen off the paper. Okay, now that's not a really formal technical definition, but it's not a bad way of thinking of it. If you're drawing a graph and you have to lift your pen off the paper to draw that graph, then it's not continuous at the point where you have to lift your pen. Or we could say a function's discontinuous, so not continuous, wherever it has holes, which is open circles, jumps, so like just a gap in the line, sometimes that happens with hybrid functions, or asymptotes, and we know there's lots of functions in methods that have asymptotes. So, example 27. State the values of x, and we've got a graph here, for which the function shown is continuous. Now if we assume, and it's probably not a great picture, but if we assume that there's sort of arrows at either ends here to say the graph keeps going off to the right and going off to the left, then starting from the left, we've got a continuous graph from sort of negative infinity all the way down here. Now we've got this sort of, looks like a hybrid function, we've got this point here where the function seems to change over, but the graph is still continuous, right? We've got defined values all the way through here, and the values are always meeting up. We don't have like a jump. In other words, in the informal sense, I could draw this without lifting my pen off the page. It's not until I get to this point here, where I've got this open circle, this undefined value, where the graph first starts being discontinuous. So what I can say is that from negative infinity up to positive 1, this graph is continuous. So it's continuous for x is an element of negative infinity to positive 1. At the point positive 1, it's no longer continuous though, so I'm going to put a round bracket around positive 1. And then we've got this sort of gap here, so there's no defined function between x is 1 and x is 2 until we get to x is 2, and then from 2 to infinity, the graph is continuous again. Now remember that if we think about this point 2 here, right, so actually I'm going to write the interval, I'm just not going to put the bracket on it yet, so it's 2 to infinity. If we're trying to think about whether it is continuous at this point where x equals 2, we would have to look at our definition again. And our definition said the function has to be defined at that point, which it is, right? The function is defined when x equals 2. But it also said that the function must approach the same value from the left and right. Now, in this question that we're looking at, there's no graph that's approaching, as the x values are approaching 2, we don't actually have any defined values of our function. So we can't say that it's approaching the same thing from left and right because there's actually nothing on the left-hand side here. So even though it's a closed circle, we don't include the 2 in the interval because technically speaking, when x equals 2, this function is not continuous. Okay, it only starts being continuous just after x equals 2 and then all the way to infinity. Okay. Similar kind of question, but being asked the other way around here. We've got a graph of a truncus, and we're actually given the equation and the picture. We know from the equation with an x minus 4 there that we would have an asymptote where x equals 4. So it's not drawn on the graph, but it probably should be. And then we're saying, for what values of x, values of x, does this graph display discontinuity? So in other words, where is it not continuous? And the graph is continuous everywhere as we go from left to right, all of our x values, and again they should go off in the negative and positive directions like this, all of our x values are giving us a continuous function until we get to this asymptote. And if you think of the informal way, well, I could draw this graph from negative infinity, well, not really negative infinity, but all the way to the left here. I can keep drawing and drawing and drawing until I get to this asymptote where I have to lift my pen off the page and then start drawing over the other side. And the point where it's not continuous is when x equals 4. So for what value or values of x does this graph display discontinuity when x equals 4? All right, there's a lot to get your head around in that section, even if sometimes when you're actually writing the answers, they're not too complicated. The thinking is the complicated bit here. So do your best, rewatch some sections if you need to, but as always, check in with your teacher if you need some extra help. Cheers.